Hello everyone. So welcome to the Vulkan fundamentals. Okay. In our last lecture, we have basically looked at the program journey. Okay, about this beginners course, and we understood how we are going to cover various topics and covering basically the very fundamental journey for our Vulkan. Now, in this, lecture, I would call it as basically the lecture one. So the first lecture was basically the preface for the entire basically beginners program that we have for for junior developers or students, right? Now this is basically the very first lecture. I will call it as basically getting started with Vulkan. All right. So this session is basically very much helpful for the beginners. Who wanted to get started with their journey into modern graphics programming and specifically Vulkan. All right. So I would say that Vulkan is one of the most powerful APIs. Okay, you can find it in modern games, simulation systems, VR applications, even mobile graphics. Okay, and I would say that it's mostly used in a lot of applications which are high performance visualization tools. Like you have basically sorry, you have basically various video editors. All right. So um, like video editors, okay, simulators, then games, and I would say 3D effects or cinematic tools. Okay, a lot of filter based, a lot of filter based applications, okay, that you'll see on your mobile. It's all about basically modern graphics. Okay, so they are making use of compute and differentiators to produce effects, and very much utilizing the graphics capability for modern GPUs. So I would say that this course is basically all about the fundamentals of our or of Vulkan. So like I mentioned, that it is skill oriented program, so we will just not cover the theory, but there would be a lot of practical understanding. There will be a lot of examples, okay, that actually I'll give you. But specifically starting with today, which is basically, I would say that this entire, like I mentioned, this is basically a beginner's level course, and what we will actually start with today's lecture is basically the we will learn basically at a very high level and an eagle's view. Okay, we will understand basically how Vulkan basically work internally. Okay, how it is basically structured for graphics application. How to build basically real time programs step by step. Okay, so that is all about this program that we will go through. Okay, so I would say that the end goal is basically how you can think like a modern graphics programmer. So you are just not building your basically applications for a specific need, but a general need that is sufficing all the requirements for your modern graphics GPU. All right. So in today's lecture, what I would say that it is basically a getting started track. Okay. So what we will try to understand today is what exactly Vulkan is. Okay. How the modern engines in today's world, they are actually utilizing Vulkan. Okay, what the development environment looks like and how you can actually run your Vulkan program. Although we are not basically setting up any Vulkan for today's lecture, but I will continue this lecture. We will try to basically set up the Vulkan in the next lecture. So I would say that today's lecture, it's completely at a higher level, which will help you to understand Vulkan better, to get a mental model, and basically it will be very helpful for your interviews to get an understanding between how basically Vulkan is different from OpenGL DirectX, and at the same time, what are basically the competitors of Vulkan. So we are basically trying to build gradually. I mean, your understanding from ground up about the modern GPUs. All right. So without any delay, maybe actually we will start with the lecture. Okay. Now I will just, repeat this slide, what this program is all about. Okay, so in our first lecture, I have actually, explained it into a very detailed, detailed slides, which that covers basically all the topics that we are going to cover. Okay, so like I mentioned that this program it's all about. I mean, if you're getting started with Vulkan, so the question that you ask is basically if you're coming from a very simple graphics API like OpenGL and you're coming to some modern graphics API, so where do I basically begin? Okay, so what you can do, what usually you do is basically you look for tutorials, documentations, GitHub repos, or basically engine, but that quickly becomes very overwhelming because there is basically a lot going on. Okay, you will set up the Vulkan, but then you see big examples, okay, verbose code. But the very important fact to understand any big problem that I believe is basically getting understanding of the fundamentals. Okay, if you have basically a very good understanding of the fundamental, then it's just like adding Lego pieces together to make it work. All right, so I would say that this entire program actually help you to basically clear your thoughts over the Vulkan. I mean, it will guide you through lectures, videos, examples, okay, and basically a lot of examples. Okay, so we will not basically just pick up any random Vulkan topic, but we will try to do it systematically. So first we will make the mental model. Okay, mental model about Vulkan, how it is used, who bring it, okay, how it's different, how underlying the drivers basically look at the Vulkan, and what is the difference between the drivers of OpenGL and Vulkan. We are not getting dwell into the drivers itself, but I will give you basically a very higher overview. Okay, why the Vulkan drivers are basically thin compared to other, and what are basically the problems that these are basically trying to solve. Okay, so we will also understand basically how all these different components fit together. Okay, and learn basically the rendering workflow into the GPU. Okay, so I would say that end of the day, once this course is completely, you would be having a better understanding of this beginners program, and then we can jump into the intermediate or advanced level of the Vulkan. Okay, that certainly we can cover into our next a games module or basically application module, okay, that we will cover. But once you have covered this entire basically fundamentals, you would be having an understanding of how Vulkan actually use the rendering pipelines, how different systems get connected, how to basically deal with performance, okay, and debugging with modern graphics. So it's all about learning the Vulkan fundamentals. All right. So I would say that my target today is basically to give you a high level understanding of Vulkan today. Okay, a very fundamental understanding of Vulkan today. So we expect the lectures is around about 45 minutes. Okay, we have 21 slides, so I guess it almost take 40 minutes. Okay, so what we will try to do is basically we will cover basically the overview of Vulkan and basically its role in modern graphics. So we can actually discuss various things like, what exactly the Vulkan is actually, solving. Why we need such a graphics API? What are the problems with the older API that we need a new API? How modern engine and applications they make use of Vulkan, or they are moving towards low level APIs. So Vulkan is basically a low level API. OpenGL, it's much more high level API. So once we actually covered the lectures today, you will understand, I mean, how it is basically low level API. All right. Now, what else we also cover is we will cover basically Vulkan with other APIs, whether it's basically traditional old APIs like graphics API like OpenGL DirectX 11, or basically the new APIs like DirectX 12 or Metal by Apple. Okay, so the important fact here is that we will try to understand, I mean, what are the high level difference, just not basically from the API perspective, but at a higher level. Okay, that will help you to basically clear your interviews, because you are basically at a very, I mean, fresher level. So perhaps there are not a lot of expectations to dwell into. But once you have basically done Vulkan, and Vulkan with a basic understanding of how the rendering pipeline works, I think that's basically makes that leaves you at a very powerful state. Okay, so certainly, like in my last lecture, actually I mentioned that if you are a graphics programmer and you don't know basics of Vulkan, okay, that is not basically very good. Okay, so I think being a junior developer or basically a graphics programmer, you should be having certain level of understanding how modern graphics work. Okay, so this is where the modern world is basically moving. Okay, now we will also understand basically how Vulkan takes basically a different approach compared to OpenGL, whether it's shaders, rendering pipelines, compute capabilities, or basically managing memory. All right, now I would say, I mean, end of the day, you will see that, or basically end of the lecture, I mean, what you will see that, I mean, Vulkan, it basically drives a lot of things. Okay, the driver layer, it's very thin, so it basically controls a lot of things. Okay, in terms of memory, in terms of rendering pipelines. Okay, pipeline state objects. Okay, shading capabilities. Okay, it controls a lot. It gives you better control, predictable performance, and basically it gives more responsibility on application developer. Okay, so I would say that there is a good programming required in Vulkan, and that is what it means, that it basically gives a lot of responsibility on developers' shoulder. Okay, so I think without getting delay into the this topic, maybe actually we can start. Okay, so now we will actually cover basically the overview of Vulkan, and we will check basically the its role into modern graphics and compute. Okay, yeah. So I mean, I would say that the very first question, if somebody asks you, is what is Vulkan, I mean, you should answer that it's basically a modern, the important keyword is basically it's a low level graphics API, or more precisely I would say it's a modern low level graphics and compute API. Okay, so OpenGL is mostly the graphics API. The later version comes along with the compute capabilities as well. Okay, so what exactly graphics? So anything that you wanted to draw on your screen, on your basically surface, okay, using the GPU capabilities, like APIs like OpenGL, we called it as basically graphics API. But at the same time, if you wanted to do some non-graphics, I mean, basically processing, like a lot of compute, lot of multiplication, matrix multiplication, and that does not need basically end of the day any, I mean, graphics output, or more or less basically if you wanted to do mathematical graphics. Okay, so for all those crunchings, compute is basically the API we use. So what exactly the compute API is available, okay, in the market, if you wanted to understand, okay, it's basically CUDA, OpenCL. Okay, all these are basically parallel compute APIs. Okay, so Vulkan actually gives you the capability of CUDA, OpenCL along with the graphics API. All right, so it basically helps the developers to directly communicate with the GPU, and basically it tried to, I would say, uh, expose more GPU capabilities now, which was not basically available in OpenGL. So in OpenGL, a lot of things are basically abstracted. For example, you cannot manage the memory, you cannot manage the pipeline state objects. You can just set them through switches, okay, like GL enable depth, GL enable some another basically parameter, okay, clear color, like that. So it works in terms of switches, but it does not gives you a direct capability to managing the hardware. But that's not basically the case with Vulkan. All right. So Vulkan actually gives you much more capability to schedule jobs and execute them on GPU upfront. So the upfront keyword is very important. So it is not getting scheduled. Okay, once you send the command, it's basically get executed upfront. All right. So this is very important when we talk about basically fine control over the performance or resource management. Now, like I mentioned, that Vulkan is just not basically for graphics, it's basically for compute application. So you can do basically a lot of number crunching that you can use for image processing. You can use it basically for scientific computation. Okay, one important thing is that uh, it is basically being used in machine learning as well. So you can actually look at the Llama C++. So Llama C++, it comes with the backend of Vulkan as well. So if you don't have CUDA, or if you don't have basically a CUDA capable GPU, okay, you don't need to worry about. You can actually use Vulkan, okay, which help you to use your existing modern GPU, and it will try to do basically all the compute applications for you, okay, all the compute processing for you. Now, one important question that actually I would say that since we are discussing Vulkan, one question that you need to understand that why fundamentally the Vulkan exists. There was basically an API which is like OpenGL or DirectX, okay, but what was the reason basically this new modern API is required? Okay, I would say that the requirement was basically for a long time, but it just that we are working with OpenGL, and over the time the GPU has evolved. They have evolved a lot, okay, and every time a GPU is basically evolved, there are new API, there are new basically theories which are upon which those GPUs are basically built. And to suffice newer APIs, we need basically some flexibility. So we want basically a Lego model which is very minimal, but it basically allows you to do anything that you wanted to do. But this is not where the OpenGL fits this criteria very well. The reason was that OpenGL tries to solve a lot of things at a very high level. So whether it's basically memory management, okay, or basically setting up the rendering pipelines, so it's very much abstracted, okay, but that's not basically a thing that the modern developers they want basically a very thin driver that allows them to basically manage the GPU the way that they want. So they can manage the queues. Okay, I will help you to understand what exactly the queues are. Okay, they wanted to help manage the queues. They wanted to help managing the synchronization. The synchronization matters a lot, okay, because we are working on CPU, we are working on GPU. There is definitely a synchronization required. Otherwise, there would be basically lag, or basically things just goes, I mean, out of order, and it create basically more chaos. Now, uh, also, the resource scheduling is basically another thing. Okay, like I mentioned that in modern graphics like Vulkan, we have only two type of resources: buffers and textures. So we wanted to manage those buffers. We wanted to manage their memory, and this is where OpenGL is not very handy, and that's basically pushed a good a reason that why we need to work with modern APIs. And I would say that Apple was the very first one who basically took this initiative, and they wanted to basically move away from OpenGL. And in 2014, if I'm not wrong, they have actually launched their Metal APIs. So their claims were that they are creating a very a modern graphics API which is thinner, and it basically very well suited for their GPUs. So they can actually program the graphics, I mean, towards their GPU capabilities, and not basically dependent upon OpenGL. The second thing that you need to also understand that OpenGL is a very old API. I mean, it started. I mean, way before 90s it started. Okay, but in 90s it basically came into an official existence. But from 90s to 2025, 26. Okay, the API still exists. And that means there is basically it's carrying basically a lot of backward compatibility. Okay, so even if we are not talking about the fixed function pipeline and we talk just about the programming pipeline, okay, I would say that it's carrying a lot of overhead of those, i mean older APIs. One example is basically buffer management, okay, or the vertex buffers. You have a lot of methods to manage the buffers in OpenGL, okay, and and that is something I would say that where it gets basically bloated. Anyone actually comes with a new idea, they create their own APIs. Okay, but that's not basically a case with Vulkan. Vulkan gives you basically a very low level access of memory and how you wanted to manage the vertex buffer. So you can create your own customized memory allocators or basically vertex buffers, and you can deal with them. So that is a kind of problem that Vulkan tries to solve. Okay, so I would say that it basically removes the bottleneck that we actually see with OpenGL, because it's very high level. I mean, it's not basically perhaps doing the correct job, and the job is actually given to the drivers, and we have basically various vendors. So they are the one who manages the memory, who manages the performance bottleneck for you. Okay, so that is basically, I would say, it's basically the core philosophy why, I mean, Vulkan was required. Now once in I mean once the metal came into existence, which is basically an API from Apple in 2014, then there was a stronger push. Okay, and in 2016, Vulkan was basically, came into existence, and from 2016 to 2026, it's almost, I mean, 10 years. So yes, it is a modern graphics API, but it's already been 10 years now. Okay, so it's very much essential for us to basically understand. And I would say that I'll encourage you to actually do more programming in this one, because that's how the market and the industry is moving towards. All right. Now I would, I mean, also cover basically a high level thing here, like maybe the core philosophy of Vulkan. I mean, I would say the core philosophy is basically it gives you the control of everything. Okay, when I say everything, it's literally mean everything. Okay, that means if you are creating an application with Vulkan, it helps you to manage your memory. You can look at various type of memories that CPU GPU gives you. Okay, you can choose what are the memory that you want. You can do the memory allocation, you can do your custom memory allocators, you can do the synchronization GPU CPU between the buffer itself. Okay, and various jobs. Okay, we will cover these things in detail. You will deal directly with command buffers and command submissions into the queue. So that level of controllability it gives. Then finally, it gives you the pipeline creation. So pipeline creation is basically graphics pipelines, okay, or compute pipeline, okay. So for your compute jobs, for your graphics job, so it gives you that kind of capability. Okay, now since it gives you a lot of capabilities, the driver is actually very thin. So you have to write a lot of code. But I would say when I say a lot of code, I mean it's a one-time thing. So usually if I wanted to create a buffer, okay, I just create a class, I do that one time programming, and then I start reusing it. And Vulkan is, I would say, it's truly object oriented. Okay, whereas OpenGL it is not a case. Okay, later I will discuss this why it is so. So I would say that with this philosophy, Vulkan gives you basically better performance, scalability, and control over the hardware that actually you basically require. So all right, now so where do we actually we start with Vulkan? So I mean, a better way to answer this question is perhaps, I mean, the very first thing is that, I mean, why such a question actually comes into our mind? I mean, where do I basically begin with Vulkan? Okay, like I mentioned that Vulkan is basically a bit verbose. So how you wanted to start, you wanted to start with something new, which is very simple, right? So you wanted to create a window application. You just create a window, give its dimensions, and behind the curtains it just create that surface and bring it. So you don't need to worry about, I mean, how that surface is created, what is basically the RGB format for that surface. Okay, and how it's basically managing that memory. Okay, so you don't need to worry about those things. So what you want is basically a very simple program. Now if you wanted to do a simple program in a graphics API, what it would look like, I mean, it would look like basically something like a very simple triangle that you wanted to draw. Okay, a simple triangle with different colors on their vertices. But this is where, I mean, it becomes I mean, a trouble for most of the people, because when they see the very first program, it just not comes with I mean, a few lines of code, but it may actually go to a few hundred lines of code. Typically, it's basically around 1,000 to, I mean, 1,200 lines of code. You may actually end up with rendering that triangle. But I would say that this is not basically something that you should be worrying, but this is something that you should start understanding, that yes, it requires a lot of programming. Okay, but this is basically a one time investment. Once you basically set up all the rendering pipelines, it's a redundant code that you will reuse, and now you have to use basically a better engineering to see how such verbose code needs to be managed in terms of classes or function, so that you can just reuse them. And once you started to reuse them, I mean, I would say the core program of Vulkan, it just reduced to very few lines. So perhaps you should be thinking in this way, that I mean, you are using Vulkan, you are basically creating some verbose code, but end of the day that verbose code should be such that you are creating an API for yourself. Okay, so you are using this Vulkan API to create your own OpenGL version, okay, which is much more compatible. Okay, and later actually I will show I'll give you some examples how I manage the engine. Okay, and how we create basically a very simple application or a framework, okay, that can be scalable to editors or basically games or application, something like that. All right, so I would say that I mean, definitely, OpenGL is easy, but it comes along with a lot of, I mean, complexity. Okay, it is easy to set up OpenGL, but when your application goes complex, it's very difficult to manage it. Okay, the driver is basically it's very fat, so it cannot handle a lot of complexities. Then managing the memory, GPU scheduling, synchronizations. Okay, it's not that easy. We all know that Vulkan is, OpenGL is basically a state-based application. I mean, state-based API. So you set the states, and the problem with the states is that, let's suppose you are writing a very complex program, and it's all about, I mean, all written with OpenGL. You have nice classes. Okay, you have hundreds of classes, But the API that you are using, it's not truly object oriented. It's basically a state based API. So although you created an object and you change something as a parameter of that object, and it internally goes and changes the state of OpenGL, it's not affecting only that object, it affects the entire pipeline, and that's make it very difficult to debug. Let's suppose you have 10 classes of 10 objects that rendering 10 different shapes, and it has basically a depth capability, and each class handles it individually. But if you mess up the depth rendering, okay, it will start basically giving you incorrect result, just not for only that shape but for all the rendering, because it's basically a state based global API. Okay, so this is basically, I would say that uh, it basically comes with a real cost. Okay, where you see that things are basically very easy, but it's not easy to manage. Okay, you can actually start it very easy, but sooner when you actually start creating a game engine and application, it becomes unpredictable. Then you will try to basically debug those things, and the debugger, it points to the driver, because that is not basically how easy it is. And if you will notice that OpenGL gives you only five type of errors where you can debug and guess, I mean, where the things are getting wrong. But that's not a case with OpenGL. OpenGL gives you a particular problem with the validation layer. So you can enable the validation layer. It will point out the line where it's going wrong. It will also point out the APIs where you are probably sending a wrong enum or using basically an incorrect number. Okay, so it's really very powerful. Okay, so we will discuss what validation layers are. The second thing is basically the transparency. So transparency, it's very important, and that's basically a promise that Vulkan does. So every line that actually you write, okay, everything that you do, it's basically provides a complete transparency. Okay, so yes, it is verbose, but that verbose comes with basically some reason, and the reason is basically something that you are writing, it's really happening on the GPU. So for example, you are writing the memory allocation, it's straight away, I mean, happening in the GPU. It provides you much more complex, and being a graphics programmer, I think that gives you a kind of confidence that you are really working with something low level. Otherwise it always something like that, you do not know what is happening. It helps you to, I mean, implement the pipeline states, recording the command buffers. Okay, so I would say that there is nothing hidden. Okay, so uh, I mean, from my point of view, I would say that I'm into this field for 20 years. Okay, and I worked with basically various APIs. Okay, various APIs from OpenGL. Okay, so all versions of OpenGL, whether it is embedded WebGL or basically higher level frameworks for that. Okay, and I worked with Metal as well, which is basically a modern graphics programming from Apple. Okay, so in that sense, I will say that Vulkan is basically uh, it's a true API that one should basically definitely learn and to get started with. Okay, because it helps you to, I mean, control the GPU the way that you want. Okay, and Vulkan becomes very easier for you once you have basically the fundamentals understanding. So you will actually see that now there is no guesswork is doing like in OpenGL. It's you who is basically controlling those application drivers. Okay, it's you who is basically controlling those entire pipeline. So I would say that it's you as a developer who is giving step by step instructions to the GPU how the program is basically going to execute, and that gives you basically a very powerful, extremely powerful capability to create basically complex rendering applications or complex basically games. Okay, so I feel that if you wanted to do a justification to your, degree, if you are a graphics programmer or something which deals with games, or an engineer who works with graphics application, I mean it's a modern requirement. Okay, if not today, then tomorrow you have to do that. The sooner you start doing that, it becomes easier for you. Okay, things are harder, but once you actually keep on dealing with day to day basis, I mean it becomes habitual. All right. Okay, so I mean, I covered this thing just in a bit, what exactly the Vulkan is. Okay, so I mean, like I mentioned, I already gave you a history that Vulkan is basically, it's released in 2010, basically 2016, after I mean Apple, they have released their Metal API. Okay, and it's basically derived from AMD's Mental API. Okay, so the original name, I would not say the original name, but the key idea was basically mental, and then mental was basically, uh, I mean, used to create basically Vulkan. Now, Vulkan, it's basically, I mean, truly, I would say, a very scalable graphics and compute API, because it simply works across CPU, GPUs on Windows, Linux, Android, and even Mac OS. Okay, so, and we know that for Mac OS we have Metal API, right? But the Metal API, it cannot work on all these operating systems like Android, Linux, okay, different Linux versions, or basically Windows. Okay, so that I would say that it's a very powerful API. Okay, so Vulkan comes with the graphics and compute. I already mentioned to you what exactly the compute is. Okay, and who are basically the creators. Okay, so the Vulkan modern graphics and compute API is developed by Kronos. Okay, so Kronos is basically, it's a consortium of companies like Nvidia, AMD, Intel, okay, Google and Web. So what they are doing, they are creating open source APIs which are royalty free, so that everyone they can basically utilize. Okay, so Vulkan makes it completely vendor neutral. At the end of the day, I would also like to add that Linux, okay, Vulkan gives basically Linux first class citizenship for the GPU API. So for graphics, earlier Linux doesn't have basically a very dedicated API. Okay, so it depends upon OpenGL, but the support of OpenGL was not very good. But Vulkan is something which, I mean, truly supports, I mean, Linux-based distribution. Okay, Ubuntu like, and a lot of basically programs that runs on the servers, they highly make use of Vulkan. Okay, so I would say that, I mean, for Linux, it's a very good news that it's basically a I mean, first class graphics API. Okay, so and it basically later supports, so every time we get this Ubuntu, we get the latest drivers. Okay, and for the SDKs and for other Vulkan related APIs, libraries. Okay, now the another thing about Vulkan is basically it's one single API that can run on Windows, Linux, Android, on and Mac OS. So you don't need basically different version. That means, for example, Android is an embedded system. Earlier, for OpenGL, you use OpenGL and you use basically OpenGL ES, okay, which is basically an embedded based version for your OpenGL. But for Vulkan, it's not that case. You have single API, you program it once and you can reuse it in your embedded systems as well. Okay. So, I mean, end of the day, I mean, I would say that Vulkan is just not basically a faster API, okay, but it's basically an API which does things basically a bit differently, but at a more low level, basically at a more low level. Okay, so it gives you basically a lot of explicit control for synchronization and pipeline management. Yeah. So in this actually slide, we will try to, I mean, take a contrast with the modern GPU and understand basically how Vulkan and OpenGL, I mean, there is a fundamental difference. I mean, with these APIs and how basically GPU has, I mean, basically evolved over the time to better understand Vulkan. Okay, so I mean, I would say that from 90s to 2006, if you will see, the hardware has changed dramatically. Okay, but the APIs, they are not keeping up with the pace at which the hardware is changing. Okay, so this actually creates basically a mismatch, and we know that for OpenGL there are basically a lot of vendors, and it's not easy to release basically a fat driver API like OpenGL, because when you release any new specifications, it needs to be properly tested. And like I mentioned, OpenGL comes with a lot of its backward compatibility overhead, so the testing time, regression time, it's a lot more. Okay, so that is also basically a reason that the older APIs, they cannot keep up the pace the modern GPU they are expecting. Now, I would say that OpenGL, the basic model of OpenGL, it's single threaded. Okay, it's not scalable to multiple threads. You cannot use OpenGL for multiple threads and do the rendering. Why? I mean, end of the day, OpenGL is basically a state machine, and it's a global state machine. Whether you create two objects, okay, the state it still can be affected. If you're creating multiple threads, okay, irrespective of one class, one object, and it's divided into two threads, end of the day, it's still using and affecting the state machine. So you need basically a better synchronization mechanism, okay, if you wanted to. Otherwise it will basically screw up the. Okay, so in OpenGL, what you'll do, you simply, I mean, set the textures, you bind the shaders, you draw the meshes. Okay, and somebody has to figure it out, I mean, how these things would run on the GPU. And who is doing that? I mean, this is something, a responsibility of the driver. So what is happening behind the scenes? Behind the scenes, the driver is basically doing a lot of work, I mean, lot of basically, I would say, the hidden work. Okay, which is based upon the state machine handles that you are giving. And I would say it's a lot of good guesswork, where they wanted to manage what kind of memory they think that it's suitable. They are basically compiling the shaders. Okay, then also, I mean, doing a lot of scheduling and tracking of those rendering states. Okay, what do you mean by tracking of rendering states? We have pipeline state objects, so whenever you change a state, there is a dedicated pipeline state object needs to set. Okay, so they need to basically keep track of those states, and once they are tracking those states, there may be basically shaders that comes into the picture, and sometimes the shaders, they just goes off the memory, and once they goes off the memory, we have to again recompile the shaders if they come into the picture again. Okay, so I would say that the driver is doing basically a lot of parallel processing in OpenGL, which is based upon a lot of state management, basically, and the hints given to the driver. Okay, so this is basically, I would say, the OpenGL model, which is basically an old model, and it's not very basically scalable. All right, and one of the most problem actually that we will see is basically shader starters. What are shader starters? Basically, what happens is that I mean, one of the big issues that these older APIs they actually deal with is basically the runtime shader compilation. Okay, so once the shader is compiled, for a number of reasons it can be recompiled. Maybe due to the VRAM it's very limited, it gets kicked out, or basically there is a new pipeline shader object which doesn't cache the older pipeline state objects, or maybe other reasons, but that is a very common problem that we have seen. So it's particularly called shader stutter. Okay, you can go and search about it. I mean, so but what exactly the shader starter is? So for example, when you play a game, okay, you are doing basically basically a lot of exploration, but what you will see that for, I mean, suddenly what you will see that there is basically a freeze of the rendering pipeline. Okay, what you will see there is basically a little freeze on your, game. But why that little freeze come? Okay, something that either requires memory, or perhaps it may be a shader recompilation that is happening, and we know that very well. We know that the shaders, they are recompiled on runtime. Okay, so, and that basically happens during the rendering at the fly time. Okay, so that is something, it causes performance degradation, and it should, and it's not basically a very good experience, I would say. And this is something what, the modern programming it tries to solve. Okay, the another thing that actually you will also see that the OpenGL, there are basically a lot of, driver heuristics. So driver heuristics, so that means, what exactly it means? Mm, just give me a second. Yeah, this is the slide. All right. So what driver heuristic means? That means a lot of work, like I mentioned, it's basically happening behind the scenes. Okay, so there is a lot of guesswork that the driver has to do when it receives the signals from the application itself. So for example, I mean, we have command buffers. Okay, when to flush those commands. Okay, when to basically reorder those things, and managing the memory, like I mentioned. So it's all basically a kind of guesswork that the driver has to do from the application point of view, and uh, we have unpredictable performance because different drivers comes from different vendors. How they do this work, it's very much depend upon the kind of hardware they are doing. Okay, so one driver, I would say that the flushing of commands, it's good, but the same, it's not very good on the other. So it actually depends upon the same API, how it is basically implemented by different drivers. Now the global state machine, it's the another problem, like I mentioned. Okay, so just now, we discussed the global state machine. Okay, that OpenGL is a state-based machine. Whether you use a single thread, you use multiple class objects. Okay, it's a global state machine, and it cannot be used basically by different threads, different objects. Okay, end of the day, it's a global state machine, and it can easily create problems. Okay, so it's not basically very scalable. And at the same time, I would say that it cannot utilize multiple cores. Okay, that, I mean, like I mentioned, for the CPU threads. Okay, and it makes it very difficult to record those command buffers and efficiently either basically compute across different CPU threads, and it becomes basically a potential a performance problem. And this is not a case with Vulkan. Okay, so I would say that Vulkan, it's truly scalable, so it allows you basically multiple threading. Okay, the last point, which is like I mentioned, that vendor inconsistency. So the same APIs, like I mentioned, they are implemented by different GPU vendors. Okay, how they implement those APIs, those drivers are completely different. Okay, and it's basically a proprietary. So that is also basically a reason you will find that you run your program, OpenGL program, on one driver, it gives basically a consistent behavior. But on some other driver, I mean, you suddenly just notice that your things are not rendering. But what you are doing wrong, you do not know. The driver, it's not capable, or capable to debug that, because there is nothing wrong, but it's basically more towards a driver behavior. Perhaps it needs basically certain type of states, okay, that you have to explicitly enable, whereas the other driver, if it is not explicitly enabled, it just takes a default value for that one. So these are basically certain problems where the OpenGL becomes very unpredictable. So vendors, I mean, what are vendors? I mean, who are those vendors? I mean, vendors are basically the GPU makers like Nvidia, AMD, Intel. All right, so I think these are basically certain big problems that you have to understand, and if you understand those, Vulkan is exactly fixing these kind of things for you. Now let's take a contrast of Vulkan compared to just now what we have seen, the older model of, I mean, OpenGL. I mean, in Vulkan, I mean, you are someone who has actually take in charge of your application. So you are basically responsible for managing your memory, compiling your shaders, okay, record the commands. Okay, so, and basically recording the command buffer, and end of the day submitting those command buffers into basically queues, okay, for execution of those command buffers onto the GPU. Okay, in the end of the day, I would say that the driver has basically very little work to do. Okay, and this actually makes the performance much more controllable and predictable, because you are the one who is managing those memory. There is no guesswork. So even if you have basically different vendors, since you are managing the memory for those different vendors, okay, it will be basically the same type of memory management that you are giving. Okay, so I would say that instead of driver making any hidden decisions or guesses like OpenGL, in Vulkan, I mean, you are the one who is basically explicitly controlling the performance and predictability. All right, now with Vulkan, one good thing that actually comes is basically predictable performance, and that is basically a huge advantage, I would say, that Vulkan gives you, because Vulkan completely removes those hidden driver operations like state management, right? So the performance becomes, I mean, much more consistent. So you don't see basically any stutter problems from shaders, okay, any unexpected stalls. The performance is consistent, there is no frame drops. Okay, and the thing is that once you basically give a job, the job handles the job basically handled by the GPU is upfront. So once you submit it, it's basically executed upfront. Okay, so there is no such, I mean, unpredictable uh, I mean, I would say unpredictable what is the right word? unpredictable operation, that something gets coming and it's basically delaying, or okay, so anything that you are doing, it's basically upfrontly executed on the GPU. So end of the day, whatever you are programming, you know that what you are doing. Now Vulkan, it's basically truly multi-threaded. That means you can utilize multiple cores from your CPUs. Okay. Whereas it's not basically a case with OpenGL. I mean, we know that it's basically suscepts with, I mean, global state. So it's not very efficient for, I mean, state locking. Okay. And in Vulkan, you can actually record multiple command buffers across different threads, which is not basically possible in OpenGL. It's not very scalable. So, what are command buffers? Command buffers are basically uh, it's basically a buffer of small commands. So, what are those commands? Those commands are basically GPU specific, or basically your graphics specific commands that you wanted to do. So they are collected into a command buffer, and then that command buffer it's given to the GPU to process. So what here actually I wanted to, I mean, help you understand that those command buffers that you are doing, you can independently do in two multiple threads. Okay. So and they will not clash with each other because it's not basically a global state kind of machine. So Vulkan, if you will start programming, you will see that it's truly an object oriented programming. Okay, so you have small structures, and once you basically set up those small structures, it create pipeline state objects. So it just affect those one. Okay, so it's truly possible that you can record multiple threads, and you can basically scale your application. And this is, I mean, end of the day, I would say that it improves the performance. So whether you are creating a simulation system, game, or any rendering system, it's highly, I mean, useful. Now the next point is basically it provides Vulkan provides you the explicit resource control. So that means it's you who are basically manage the memory by themselves. Okay, so you can manage memory heaps, you can basically allocate where you want it to do the allocation. Okay, also it is in your hand when you wanted to destroy your basically resources. So there is nothing, I mean, which is hidden in the driver. Okay, so it's you who is one basically managing your heaps, allocating them, and destroy them when you are not needed. So what exactly it helps you? It actually helps you to make your performance predictable. So for a performance based application, we need basically, we wanted to use memory pools because memory allocation, it's a very expensive operation. All right, you give it the command from CPU, then it goes to GPU, GPU gives it and come back to CPU. So that is not something that you want. So usually we have memory allocators, memory pools for those kind of things. Okay, so I would and end of the day, I would say that it gives you an explicit resource control. So it helps you to basically avoid memory spikes, any unexpected driver allocation. Okay, so your basically application becomes more predictable. It's more visible and control. In control of you. Vulkan, it's basically truly one API. Okay, like OpenGL and OpenGL ES, they are not basically different versions that you require. In fact, OpenGL also have a web version that you don't require. So you just need basically one API, and that makes the I mean the Vulkan uh, for, I mean, a very basically optimum choice for the vendors, because the driver is thin. They don't have to do a lot of programming. At the same time, they don't need to manage in versions like OpenGL, OpenGL ES. Okay, so there is no Vulkan ES. Okay, there is no Vulkan WebGL. There is only one API. So it makes the entire process much more basically faster. So they are not different basically versions of the same API which is released. Okay, so end of the day, if you wanted to understand, I mean, OpenGL Oh, so this is a program. Oops. OpenGL. Okay. Then here, right, Vulkan. Vulkan API. Okay, this is OpenGL API. All right. So in Vulkan API, let's check the. So in OpenGL API, so this is, I would say that this is the entire application that you are, or basically your program that it's running, and your program it's running with the help of application and the driver. Okay, but if I wanted to create a boundary, I would say that this is your application, and this is basically the driver. The driver it's really very fat. Okay, whereas in Vulkan, this is basically opposite. Perhaps you have this application and this is your driver. The driver is very thin. Okay, so it's a best choice for your different vendors, okay, to go with such API. So they need to release very thin API, and they can release very frequent releases for your Vulkan. Okay, whereas in OpenGL, since the driver it's basically fat, it's not very easy to, I mean, release the APIs. Okay, it takes a lot of time. Okay, at the same time you need to write basically very small code in OpenGL, whereas the code, if you will see, I mean, it's basically a lot more compared to OpenGL. But that truly pays off. Why it pays off? Just because the advantages that actually I mentioned just now, the advantage that we discussed over OpenGL. All right. So this is basically, I would say, the big difference between an OpenGL application and a Vulkan application. All right. So let's move to the next slide. All right. So in this slide, we wanted to basically look at the other competitors for Vulkan. I mean, definitely the older competitor, I would say. I mean, it's not the competitor, I would say that, but it's just, I would say that the new generation of OpenGL from Kronos is basically Vulkan. Okay, and just now we have seen how it is different. But since we are now, I mean, dwelling into more modern graphics API, we wanted to understand that are there any new APIs other than Vulkan that follows the same model, okay, which is basically the modern low level graphics API. Okay, so yes, Vulkan is just not alone, but there are basically competitors like DirectX 12, Direct and Metal. So Metal is basically from Apple and DirectX is basically from Microsoft. Whereas Vulkan is basically from Kronos Group. Okay, so Kronos Group, like I mentioned, it's a consortium of companies. Okay, so Valve, Google, Nvidia, AMD, and any other, I mean, GPU, I mean, makers, they are basically a part of it. They are creating royalty-free APIs, and what they are actually bringing is basically Vulkan to us. Okay, now these are basically modern APIs, but there are basically some, I mean, differences. So what you will see that, I mean, Vulkan is basically the coverage is basically a lot. I mean, it basically runs on Windows, it runs on Linux, it runs on Android. Okay, in fact, it can also run through on Apple. Okay, so how does it run on Apple? I mean, there is basically an implementation called Molten VK. What it does, it's basically it use Vulkan APIs and it then converts it into Metal API. So that is how the Vulkan runs on Metal, on Apple using Apple's Metal API. But there is basically a one-to-one mapping, I would say, of Vulkan that it's did for a Metal API. So that makes it basically really scalable. So Vulkan, it's capable of running Mac OS, okay, through Molten VK that basically converts Vulkan commands to your Metal commands, okay, Metal API commands. And this is how actually you can run. So you can create one Vulkan application and you can run it on Metal as well, okay. Sorry, Apple as well, Mac OS or iOS, okay. So on the other hand, DirectX, it supports DirectX 12. It only runs on basically Windows, and basically it's compliant like Xbox. So you cannot run on any Linux or Unix variants, okay. You cannot run it on Android or Mac OS, okay. So there is basically a larger compatibility. So from a company point of view, from an organization point of view, they don't want it to hire basically three different developers. Unlike the company, it's really profitable and they are very specific about, I mean, their the performance. So definitely I would say when you are running Vulkan with Mac OS, okay, so it may not be basically as good as Metal, but certainly it's not as bad as that you cannot see. I mean, you can observe basically, I mean, basically problems. So there is no problem. I have tested it and it runs beautifully. Okay, so I would say that, I mean, based upon these, you can actually you can see that Vulkan is basically an API that perhaps you wanted to choose if you wanted to go for a modern low-level graphics programming. All right. Now this is basically a high-level. I mean. Uh, a mental model of Vulkan. So how Vulkan is basically, I mean, it's basically different with other APIs. Okay, and what exactly the overall, I mean, mental model for it. So what exactly the mindset shift? Okay, so here actually what we will cover is basically we will cover, I mean, how Vulkan is basically is an explicit API. Okay, so what we will compare is basically we will compare implicit and explicit APIs. Okay, and we will try to understand their differences. Okay, so what are basically implicit and explicit APIs and how, I mean, they are different. Okay, now I would say that the main difference between the implicit API and explicit API is, I mean, how basically they work. Okay, the second difference is also basically about basically I mean the implicit and explicit is how basically Vulkan basically it use it. So we can actually look at side by side on your screen. So maybe actually we can start with the implicit model. So OpenGL, we called it as the implicit model. Okay, why we called it as an implicit model? Because it is basically a state based machine. Okay, so in this implicit model, okay, the application, what it does is basically it simply gives the hint, or it simply tells the system that what exactly you want, and then it's basically a job of driver to do all the gymnastics and basically figure out how to do it. For example, it could be enabling of a shader, drawing a mesh, or dealing with textures or binding textures or vertex buffer. So it's all its job to go and basically map the VO IDs, VO VBOs, okay, all things. So I would say that behind the scene, the driver it's doing a lot of basically tasks for the driver is basically doing a lot of tasks which are basically perhaps hidden from us, and it's executing a lot of commands and performing those. So it's pretty much implicit. So it's not in our control. Okay, so like I mentioned earlier, that the same driver is basically helping you to do manage your memory, scheduling work, allocation buffers, or validating commands. So from a developer perspective, it looks easy, okay, especially if you are a beginner. So that is where this implicit, I mean, API helps you. I would say that coming from OpenGL and going to Vulkan, it gives you basically a very good advantage, because now you have an understanding what a graphics API, how it works. So transiting it to Vulkan, it makes it more easier. But if you don't have any experience in OpenGL, then I would say that transitioning to Vulkan, it may actually take more time. Okay. Now the another problem with the implicit model is basically also the runtime shader compilation. Okay, like I mentioned that we have seen basically shader stutter problem. Okay, so suddenly the frame drops because there is a recompilation happening on the on your program at runtime. Okay, so these are some of the problem that comes with the implicit API, because that is not completely in your control. The another thing is the memory placement as well, that is also not in your control. Okay, so you have a very little control over the memory behavior. Okay, and that basically, creates a great gap. So since you don't have the control. Okay, now Vulkan, if you look at Vulkan, it's much more explicit. So I don't go into a deep, because we will learn these over the time. But quickly, I will actually help you to understand, when we say Vulkan is explicit behavior, that means you are actually recording your commands into the command buffers explicitly. You can record those commands into different command buffer. You can choose what the queue that you wanted to do. We will understand what exactly queues are and how the GPUs they advertise them. Similarly, the GPUs they also advertise various type of memories, and you can actually do that. At the same time, Vulkan helps you once you choose the advertised memory, use advertised queues. Okay, you can actually create your pipeline, you can assemble your pipeline. The shaders are basically not implicit here. Okay, so you don't recompile them on runtime. So this is very different. So there is something we called it as spirv, spirv. Okay, the shaders are basically compiled into spirv before the program runs it. Okay, that means there is no runtime compilation. So what exactly spirv? I would say that spirv is basically a binary conversion of your source program. Okay, and it's not truly a binary conversion, it's something like LLM. Okay, so where your code is basically converted into a binary form, which is intermediate form, and this intermediate form is given into the program, and based upon your machine type, then it is basically converted into a low level thing. All right, so this is where it solves the stutter problem, where there is no runtime recompilation. Also in the explicit behavior, I mentioned that you can manage your memory, you can create your own allocators, you can choose the type of memory heap that it advertises. Okay, also since you are dealing with a lot of command buffers with CPU and GPU, you can do basically explicit synchronization between different command buffers, different queues. Okay, CPU, GPU, and all sort of thing. Okay, so in end of the day, I would say that uh, a very transparent way how you actually program it, and it doesn't hide anything. So that is why we also called it as basically explicit API. The another important fact is basically when you develop with Vulkan, Vulkan actually gives you validation layer. So what is validation layers? When you are basically in a development mode, you turn on these validation layers. So what it does, it's basically there are no runtime checking of the uh, uh, so in the developer mode, if you turn on the validation on the runtime, your APIs are always validated. You are checking for errors, you are checking for incorrect usage when you are doing the development. Whereas it is not an option in OpenGL. If you have validation, if you have error checkings, irrespective of development mode or release mode, you are always doing that. However, if you are creating a release mode, you can turn off these validation layers. And the interesting feature is that there is no performance overhead when you basically build a release, okay, because these layers are basically disabled. Okay, so it gives basically a developer, I mean, I would say, uh, a very safe environment when they are developing, but at the same time when they are releasing, they are basically giving them basically a true performance that they need in the production. We have already covered the multi-threading earlier, so I don't need to cover it. So what you can do is basically you can create your own command buffers, own command pools into different threads, and you don't need to deal with the global state machine like OpenGL. So you can truly utilize your multiple cores. So I would say that the takeaway is that OpenGL, it's basically implicit API. I mean, it's simple, but it abstracts a lot of things. But at the same time, Vulkan is explicit. It gives you basically a true control. There is a transparency, okay, and it's truly meant for predictable so behavior. That means when the predictable behavior comes, that means it becomes truly performant. Now this is basically a side by side comparison of your uh, OpenGL and Vulkan. So maybe I don't need to go from it. I mean, go for it because I have already covered it. But this is basically a simple small table. So whatever actually I explained to you, okay, it's a small table that helps you to memorize. So you can easily memorize it. Okay. So I'll just cover it quickly. So for your controls, OpenGL is implicit, Vulkan is explicit. The driver control, the driver is basically the driver. It's very fat. In Vulkan, the driver it's very thin. It's just basically doing the minimal things that you want. Multi-threaded, yes. OpenGL it's not, and Vulkan is definitely. I mean, there are other differences. Okay, that you can actually go through this one. So I'm skipping this slide as I have already covered it. So it just I would say a cheat sheet for you to just keep it in your mind. Now this is where the architecture diagram of implicit and explicit comes. Okay, so if you'll see the upper model, so I can actually divide this thing into two. Okay, so this is the so so this is basically the OpenGL stack, and this is basically the Vulkan stack. Okay, so I have already covered it. Okay, but I'll truly, I'll quickly go through this one. So this is basically your application code. Just give me a second. All right. So, if you look at the OpenGL application stack, what you will see that the application code, I mean, uh, sorry, if you'll see the application code, the the application code, it's really the application code, it's really thin. So this is basically the application code. This is this much, whereas the application, the OpenGL driver, it's basically a lot going on. So what it's doing, it's basically managing your states, it's doing the memory management, scheduling, validating, and all the heuristic, the guessworks that exactly it's doing. Okay, so it's quite thick compared to this one. If you will see the application code, it's basically you are the one who is writing this, so you are doing basically memory allocation, syncing, pipeline creations. Okay, for graphics or compute, you are recording your command buffers, validating logic, and you are giving it to a GPU and get it executed upfront. So you can see that there is basically a good thick level of programming that you have to do, but at the same time you will see that the driver it's very thin. Okay, the GPU hardware, it's basically the same way hardware, but you can clearly see that the overall execution required by the OpenGL driver and Vulkan driver, it's very different. And Vulkan is basically much more cleaner. Okay, so there are no basically hidden tasks, and that is why actually we called it as basically an explicit API. All right. Now this is the online and offline compilation. Okay, for shaders. Here also, I mean, we have two things. One is basically the OpenGL model. The another one is basically the Vulkan model. Okay, so what does it basically mentions? It mentions that in OpenGL we take basically the shaders as a source code, then we compile that shaders, which is basically a source code. It's basically into the text form. It converts into the low level basically binary, but that needs basically the drivers to compile this GLSL source code on runtime. Okay, and then how it is basically you draw using the shaders. Now it is also susceptible to stutter problem because your program may not be shader ready. So over, although you have compiled it once, okay, due to various reason it may actually go offline, or it needs basically compilation of shaders because the states has changed. Okay, so there could be n reasons for doing that. Okay, but this is somewhere, I mean, I would say that the problem comes with OpenGL where it needs to do a runtime compilation. Now the Vulkan is basically compiles the shaders using a utility called gslang. Okay, I forgot the name of the tool, what it's the, I mean, that it use. uh, it's called gslang validator. Okay, so what happens here is that during the build process, the developers, they write their shaders in gsl. Okay, you are still writing your shaders in glsl. Okay, in fact you can write your programs of shaders in uh, Vulkan in another shading language as well. So it's not necessary that you have to use GLSL. If you are very good in HSL, you can write your shaders in HSL, and you can basically compile through it using GSlang validator. What it does is basically it gives you a binary format, and we call that binary format as basically, we call that binary format as Sphere. Okay, the tool that it uses, this is the tool, this is the, this is basically an executable. Okay, so you give your HSL to this guy. Okay, HSL or GSL, whatever. Okay, you can give any other shading language as well. In fact, you can give the metal shaders as well. Okay, should not be a problem. And you can basically give it to SPR. So when the program runs, what it does is basically it the Vulkan simply loads this pre-compiled shader binary, and it create the pipeline. So there is no expensive pipeline compilation here. All right. Now, what exactly the SPRV? The SPRV full form, it stands for. Let me write it here. It stands for Standard Portable Intermediate Representation for Vulkan. Okay, so the V comes from here, the R comes from here, the I comes from here, the S comes from here, and the P comes from here. Okay, spirvi. So that is basically, it's an intermediate representation. So what it helps you basically, it compiles your shaders which are into text form into the binary form. Okay, and it's something like that object files that you use for your C++ programs, right? GS lang validator, like I already mentioned, what it does, it's basically it changes your source compile to the basically spirvi. Okay, it's a part of Vulkan SDK. So when you download the Vulkan SDK and basically install it, okay, you will get these all tools. Okay, so end of the lecture, I will also help you to today get started with Vulkan. So I will share some of these scripts that you can actually use, or you can basically follow up the next lecture if you wanted to basically uh, set up the Vulkan manually. All right. Now with this one, I think we are almost at the end of our slide. This is the last slide. Okay, and here what we are actually doing, we are comparing the memory models for the Vulkan and basically the OpenGL. So this is the Vulkan model, and this one is basically the OpenGL model. So in OpenGL, you manage the vertex and textures through buffers, okay, and but they are not directly in your control. You give them hints and size and the format, and behind the scene, it tries to basically decide what buffer would be, what memory would be good for you, and from there actually it manages. Okay, so stutter problem could come here as well. So yeah, and on the memory model, I think this is much more explicit, which I have already covered it, and we will see it later. Okay, so Vulkan also provides basically the VMA.